Good evening and happy Thursday. Might be a short day today. Just two things on the docket to look at. We're going to look at L'Hopital's rule and extrema. So L'Hopital's rule. And so consider the limit as x approaches a of f of x over g of x, where a could possibly be infinite. If you get indeterminate forms 0 over 0 or infinity over infinity, then that limit is equal to the limit as x approaches a of f prime of x divided by g prime of x. So what L'Hopital's rule says is if we get an indeterminate form of 0 over 0 or infinity over infinity, we can take the derivative of the numerator function and the derivative of the denominator function and then try to reevaluate the limit. So we're going to be using L'Hopital's rule to evaluate several limits. If we plug in pi, we get 0 over 0, right? So L'Hopital's rule applies. And what it tells us is our new limit now is the derivative of the numerator function. So derivative of sine divided by the derivative of the denominator function, which is 1. If we plug in pi now, we get a limit of -1. So there's our limit. And plug in pi over 4. We'll get 0 over 0. So we can use L'Hopital. We don't have to actually here. All right, so I'm going to use L'Hopital first, then we'll look at a different method. Okay. So we need to take the derivative of the numerator function. Right, cosine of x plus sine of x divided by the derivative of the denominator function. -2 sine 2x. Now try plugging in pi over 4. In the numerator, we get just square root of 2. The denominator is going to be negative. Sine of pi over 2 is 1, so just -2. Negative root 2 over 2 is our limit. Second method is just algebra. Cosine of 2x Cosine squared minus sine squared. That's obviously a difference of squares in the denominator, right? If we factor out a negative from the numerator, we can write it as cosine minus sine. Right, and then we have cancellations. Plug in pi over 4 now. And you get negative 1 over root 2, which is the same thing. Why is there an equals here? Who knows? What's going on? Oh. Now remember, we're approaching 0 from the right this time. But it doesn't matter. L'Hopital's rule still applies even for one-sided limits. We're going to get 1 minus 1, 0 over 0 squared, 0. So L'Hopital's rule applies, right? We get 0 over 0. Derivative of the numerator function, e to the x. Derivative of the denominator function, 2x. If you now plug in 0 from the right, you get 1 over 0, right? But since we're coming from the right, that is infinity. That looks like a better infinity anyway. All right, so limit as x approaches infinity, x to the fourth over e to the x. You're going to get infinity over infinity. That is a L'Hopital form, right? For x cubed over e to the x. You still get infinity over infinity. L'Hopital again. Still get infinity over infinity. L'Hopital it again. All right, still infinity over infinity. L'Hopital it again. We no longer get an indeterminate form. This limit is 0. Right, e to the x over x squared, that limit is infinity over infinity, L'Hopital form. It's still indeterminate. We no longer get indeterminate form. This is just an infinite limit. All right. What about now e to the x over 3 to the x? It is infinity over infinity, right? So it is L'Hopital form. Derivative e to the x. E to the x, right? So every higher order derivative of e to the x is also going to be e to the x. Okay. Derivative of 3 to the x, 3 to the x log 3, right? So if we take the nth derivative three to the x log of 3 all raised to the nth power. Notice that no matter how many times we take the derivative, we will always have an e to the x over 3 to the x, which means we will always get infinity over infinity. L'Hopital's rule does not work here. But what if we rewrite it instead? E over 3 all to the x power. So what's happening is we have some number, right? And its power is increasing. Well, we know something. This is going to give us three possibilities. Yeah, three possibilities. It's either 0, 1, or infinity. Right? If n is positive less than 1, then we get 0. If n is 1, we get 1. And if n is larger than 1, we get infinity. Which of those three scenarios do we have here? Right? E over 3, is that equal to 1? Well, clearly not. Right? E is not equal to 3. So it's going to boil down to, is E less than 3? Or is E greater than 3? Because if it's less than 3, then this limit is 0. If it's greater than 3, this limit is infinity.
E is less than 3.
E is less than 3, right? It's what, about 2.78? I think 2.781, something like that.
Yeah.
So you're raising a value less than 1 to higher and higher powers, right? That's 0. That has to be 0. Right. This one, very similar idea. Right. Every derivative will be e to the x. So the nth derivative is e to the x for the numerator. For the denominator, nth derivative would be 2 to the x times log of 2 all raised to the nth power, right? So again, we're always going to have that e to the x over 2 to the x. So L'Hopital's rule is never going to work. All right, so write it as e over 2 all to the x power. Zero if the base is less than 1. 1 if the base is 1. And infinity if the base is larger than 1. Well, again, e and 2 are not the same, right? They're different values. So again, it's going to boil down to, is e larger than 2 or less than 2? But we just said e is 2.781. It's larger than 2. So this limit is infinite. The limit of over x as x approaches infinity. Well, we know what the limit of the denominator is, right? That's infinity. So the question is, what's the limit of the numerator? So what does log of x do as x increases without bound? It also increases without bound, right? Albeit very slowly, but it's still increasing without bound. So this is infinity over infinity, right? It is L'Hopital's form. Take the derivative of the numerator function, right? Derivative of the denominator function. Now try evaluating it again. 0 over 1, 0. Okay, well, what happens if we square log of x? Is that going to change the limit? Let's find out. we still get infinity over infinity, right? Derivative of the numerator function. General power rule. So 2 times log of x, and then times the derivative of log of x. This gives us 2 times the limit as x approaches infinity of log x over x. Didn't we just evaluate that limit? Okay. And we said that limit's 1. I'm sorry. We said that limit's 0. So squaring the log of x didn't change the limit. And in fact, what you should notice is that no matter what power we raise it to, it's always going to be 0. Let me rephrase that. No matter what integer power we raise it to, it's always going to be 0. All right, what about x approaching negative infinity, right? Negative infinity of x times e to the x. Well, first off, this isn't even proper form, right? For L'Hopital, has to be a function divided by a function, right? And then both limits have to be either 0 or infinite. Well, can't we rewrite x times e to the x as x divided by e to the negative x? Yeah, all right. Now, if we do negative infinity, don't we get negative infinity over infinity? We can use L'Hopital. So derivative of the numerator function. Now take the derivative of the denominator function. Negative e to the negative x. Rewrite it. I don't know why I did negative x. It's just e to the positive x. Now, what is that limit?
Zero.
Limit 0. Okay. Well, this definitely doesn't work with L'Hopital. We're going to get 1 to the infinity, actually, which is indeterminate. So we're going to have to do something. I don't know why I'm doubting myself. I don't know why I doubted myself. Okay. Well, can't we write it this way? E to the log. And then properties of log says this. Now what I'm going to do is write this this way, right? So exp exponential. And that's just so I don't have to try and write what I'm about to write as a power. Remember that composite function theorem? So provided that the limit exists, it's just e to the limit of the power. So let's take a look at that limit. We approach 0 from the right. Limit of the numerator is natural log of 1, which is 0. Limit of the denominator is 0, right? So this is L'Hopital form. Now that limit, isn't that limit just 1? So this limit is e. Okay, so what about this one? I think there's actually 2 ways to go about this. So first, we can try to approach this the same way we did the previous problem. I think, maybe. Let's see what happens. I don't know why I did over X. Should be X times log of sine X. And we can write this as natural log sine of X over X inverse. No, that's not going to work. I don't think you can use L'Hopital on that, right? Because it's not 0, 0, or infinity over infinity, unless I'm remembering L'Hopital's rule wrong. Which is a distinct possibility. Oh. I'm sorry. The limit of the denominator is infinity. So we get negative infinity over infinity. Okay. Can't even accuse this on being a Monday morning because it's basically the end of the week. Oh dear. All right, so L'Hopital's does apply. Right? Numerator function, the derivative cosine of x over sine of x. Derivative of the denominator function would be negative x to the minus 2. Tangent of 0 is 0, right? And then x squared limit of that is also 0. So this is just 0. So this limit is e to the 0, which is 1. Second method. For all real numbers x, sine of x is between -1 and +1, right? So -1 to the x would be less than or equal to sine of x to the x, which is less than or equal to 1 to the x. Think about that. Is that true? I actually, now that I look at it, I don't think I can use squeeze theorem here. Because of that, yeah, I'm not going to be able to do this. So I had to do it the first way. Because that's not true for all x. Right? Because, for instance, I can easily come up with an x where that's not true. X is a half. -1 to the half is not defined in the real plane. So there's only one way to do this. It was this method here. Okay, this time, we're approaching infinity. Right? So we already did this function where we're approaching 0 from the right. Now we're approaching infinity. Right? Let's see what happens. Right, so we're going to pretty much proceed the exact same way. Right, only difference, of course, being we're approaching infinity instead. Plug infinity, you are going to get infinity over infinity. Right, so when we use L'Hopital's, this is our new limit. And this limit is 0, right? Because 1 plus x is in the denominator, and it's going to grow without bound. So this limit is e to the 0, which is 1. Okay. Well, what if instead of 1 plus x, it's 1 plus x squared? Is this going to make a difference? Well, proceed the same way. Oops. And so now the limit that we're looking at is this limit. It's still infinity over infinity, so we can still use L'Hopital's rule. Look at the numerator function first. Derivative of the 1 plus x squared is 2x. We divide that by 1 plus x squared. Right, then it's over the derivative of x, which is just 1. Which still gives us infinity over infinity. So we do L'Hopital's rule again, and we get 0. So it didn't change it. Limit is still 0. I'm sorry, limit is still e to the 0, which is 1. Okay. Limit as x approaches infinity of x times tangent of 1 over x. Well, let's rewrite this as tangent of 1 over x inverse. This will give us 0 over 0. So we can use L'Hopital. Derivative of the numerator function, right? U prime times secant squared of u. So we want the derivative of 1 over x, which is negative x to the negative 2. Then secant squared times 1 over x, or secant squared of 1 over x, all over negative x to the minus 2. This just leaves us with the limit of secant squared of 1 over x, which is 1. Why is this taking so long? Are there any questions? And we're back. Finishing up with extrema. And I want to do the same thing, right? We want to label each point absolute max, absolute min, local max, local min, or none of them. All right, so look at point A. absolute min. What about point B?
None.
Gonna be none, right? What about point C?
Absolute max.
Oops, what's going on? What about D? Would also be none, right? And then finally, what about E? And this would be a relative min, right? Just realized I'm going to do something for these. Okay, but what if we're not given a graph? We're just given a function. But what we will do is first consider how to determine absolute extrema on a closed interval. In our next meeting, we're going to look at how we can then determine relative extrema more broadly. First, this is the extreme value theorem. All right, so let f of x be continuous on a closed interval I. Then f of x has both an absolute max and an absolute min on I. From May's theorem. All right, so suppose that f of c is an extremum on a closed interval I. Then C is either an endpoint of the interval or a critical point of F.
Leah, one, you want to go to your room, then stop, try and stop. Zion.
Right, so critical point C is any point in the domain of the function such that the derivative at that point is 0 or the derivative at that point does not exist. Right, so if we go back and we look, let's say right here. No, this one's going to be better. Right, B is a critical point. It has a slope of 0. Right, that's its tangent line. At C, it's also a critical point, but in that case, the derivative does not exist. Right? So if you meet at a cusp, right? So if the point is a cusp, then the derivative does not exist at that point. Right? Again, here F, you notice the tangent line is horizontal, so that has a derivative of 0. And then, of course, in this case, we also had these two endpoints here, right? So that's what Fermat's theorem is saying. So that all of your extreme values will occur at critical points, or if it's a closed interval, endpoints. So this gives us a way of finding absolute extrema of a continuous function on a closed interval. First thing that we do, find the critical points. All right, so to find critical points, we first need the derivative. We look for points where that is undefined. Well, it's defined everywhere, right? It's a polynomial. So now we just set it equal to 0 and solve. We can divide by 3. Can that be factored? 5 and 2 will work. So we get critical points -2 and 5. We throw out -2 because it's not in our interval. Now we test all of the critical points and the 2 endpoints. So start with x equals 0. F of 0 is 3. F of 5. It's going to be -269 over 2. And then finally, f of 6. Which is -123. Now we look at these values, right? So we look at the f of x column and we go, which is the largest? That's our absolute max. Now look at the values. What is the smallest? That is the absolute min. Okay. So now what about 3 sine of x on pi over 4 to 2 pi over 3? And again, first we need critical points. So first we take the derivative. It's defined everywhere, so set it equal to 0, solve. Cosine is 0 at every odd multiple of pi over 2. And so pi over 2, 3 pi over 2, so on and so forth. We only want the values that are between pi over 4 and 2 pi over 3. And there's only one of them. It's pi over 2. All right, so again, now we test the endpoints and critical points. Pi over 4. Three root 2 over 2, right? Next up is pi over 2. And then 2 pi over 3. And so the absolute max, we just look for the largest value. It's obviously 3. Now we want the smallest value. Well, that's going to boil down to what's smaller, root 2 or root 3? Okay. So I need to take care of something real quick. So just start working on this one, and then we'll take a look at it when I get back. Okay. Now the camera's working. Okay. So we take the derivative, right? It's a product rule. It'll be what? It should be negative. And it looks like we're going to have in the numerator 8x minus 3x cubed. Yes. All right, so we look and we go, this is undefined at plus minus 2. But those are already the endpoints. So that doesn't give us any kind of new information. So now just set it equal to 0 and solve. Solution is 0, and then plus or minus square root of 8/3. I'm also going to write down, just for completion, where it's undefined. So the question is, right, obviously 0's in the point, is in the interval, right? But what about negative root 8/3 and positive root 8/3? Well, they are, right? So this gives us 5 points to test. -2 is easy. 2 is also easy. And 0 is easy. Now, what about plus minus root 8/3? Oh, plug it into a calculator, right? You'll get 16 root 3/9 for both of them. So the absolute max occurs at 2 points. Notice that I'm not saying that this function has 2 absolute maxes, right? Because that's impossible. This function has a single absolute maximum. That value is 16 root 3/9. It just happens to occur at 2 different points. Right? And the absolute min, right? Again, not saying there's 3 of them. There's a single minimum, absolute minimum, and that's 0. It just happens to occur at 3 different points. Right? And then this is the last one. Do this one. Now, derivative is a quotient rule. All right, let's simplify this. And so it looks like numerator we're going to be left with 10x. All over x squared plus 5 quantity squared. All right, so notice first that this is defined everywhere. So now we just set it equal to 0 and solve. Well, that's easy. That means that x has to be 0. All right, so now we just test it at the endpoints. It's terrible. The endpoints and the critical points. F of -3. 9 over 14. All right, f of 0 is 0. And then we get what? 25 over 30. So 5 over 6. The min is easy, right? That's 0, 0. What about the max? Right, so the question is, which is larger, 9 over 14 or 5 over 6?
Five over 6.
5 over 6. So that's your max. Do we have any questions? Okay, so you have 2 assignments on Mount Auburn Math that will be due Saturday night, all right, the 5th of August. And then the 7th quiz, which won't be due until the start of class on Monday. All right. Now, I want you to notice, if you haven't looked at the schedule lately, I did update it because I forgot to put in optimization. So optimization is added for Monday evening. And that will also happen to conclude the third unit. So what we're looking at on Monday is intervals of increasing, decreasing, and then intervals of concave, convex. That is grouped together as the shape of a graph. So what this is going to allow us to do, which we're not going to cover this semester, but you could use increasing, decreasing, concave, convex, plus some of the basic information about the function like domain and range and where it has asymptotes and all that to sketch the graph of any function without technology. Optimization is an application of increasing and decreasing and extrema. Right, so optimization, when you look to optimize something, so you're looking to either maximize it or minimize it. Okay. That is what we're going to look at Monday evening. Next week also happens to be the last full week of the semester. Right, so we're almost done. Have a wonderful weekend. I will see everyone again Monday evening at 6 p.m.
Thank you.
Thank you. Thank you.
So looking at extrema, right? Okay, seriously. 1, 2, 3. Extrema or extreme values. Singular is extremum. You have two categories. You have absolute or global, and then you have the relative or local. F of C is an absolute maximum of f of x if f of C is greater than or equal. How do I want to do this? Yeah. I'm not even going to do f of x. I'm going to go of f. If f of C is greater than or equal to f of x for all x in the interval. Right, and obviously absolute minimum is just f of C is less than or equal to f of x for all x in the interval. Relative. F of C is a relative maximum of f if there exists some interval no why I'm writing out such that f of C is greater than or equal to f of x for all x in that interval. And then similar definition for relative minimum. So we're going to identify each point, each marked point as absolute max, absolute min, relative max, relative min, or none of them. So look at A. This is none of them, right? Because the point A is not defined. Now look at B. This would be an absolute max. That is the largest point. Right? Largest value on the graph. Now look at the point C. This is a relative min. It is not the smallest value on the graph. Right, you can see there are definitely values below it. However, you can find an interval where it is the smallest value. Right, it's the smallest value within that. Now look at the point D. This is again none. Right? It is not a defined point. Look at the point E. It is none of them. Right? There are values above it, there are values below it. So it can't be absolute max nor absolute min. And no matter how small we make that interval, no matter how much we shrink that disk, it will never be the largest or smallest value, right? You're always going to have values above and below. So it can't be a relative either. F is a relative min. Right? It's not the smallest value. There are values below it. However, you can find an interval where it is the smallest. And finally, G. It's a relative max. Right? There are values above it. That's why it can't be absolute. But you can find an interval where it is the largest. See that? So why don't we do this? Let's go ahead and take a break. Give you 15 minutes. We'll come back at 7:50. We'll finish up. It probably won't be too long after 7:50. I think there's only 4 problems left of this. So it is looking like it's going to be an early let out night, which is perfectly fine. All right. So we'll come back at 7:50. See you then.